Hello YouTube, welcome to a video about bipolar transistors and diodes. And for diodes we actually need a semiconductor, so we are first going to have to talk about semiconductors. And semiconductors is actually quite an easy topic, because we actually just need a material that conducts if we treat it and doesn't conduct if we don't. And we have a certain group of elements that does this, that has this property. And that's actually the good semiconductors, which are carbon, silicon, germanium, tin, and lead and fluoranium. Fluorurium, sorry. And all of those have 4 electrons on their outer shell. And that's why they are good diamonds. Carbon, for example, we can have it as a graphite and there's something else, and we can also have it as a diamond. And we could use this diamond form of carbon, but it's quite rare and expensive. So we actually use another one, which is silicon. We actually use silicon because in silicon O2, it's in its diamond form, and there's so much silicon O2 out there, so that's about 1/4 of the mass of the Earth, because it's actually all of our rocks and all of our sand and most of our glass actually is made of silicon O2, so, or silicon dioxide. So it's actually our first choice because it's so common and so inexpensive. Germanium is a bit rarer than silicon, so it's actually our second choice, and tin is actually 10 times more expensive than silicon, so it would be our third choice because it's so expensive. We can't use lead because it's noxious, and we can't use flerovium because it's radioactive. So we actually are stuck with the Si crystal, or the silicon crystal. So let's look at the silicon crystal. The silicon crystal, as I said, needs either +4 or -4 electrons until the octet rule. We're only going to look at the case +4 electrons because that's the important case. And for the case that it needs +4 electrons, it actually needs 2 bonds. 4 bonds, sorry. And why does it need them? Well, it actually has 4 electrons on the outermost shell, but it actually would need 8 to be on the perfect state, because having 8 electrons on the outermost shell is the goal for all atoms except for 2, which are hydrogen and helium. But for all other atoms, actually the goal is to have these 8 electrons on the outermost shell. So we have 2 electrons on the 3s shell, or the 3s orbital I should say, and 2 electrons on the 3p orbital. Now if we draw that, and I can't really draw well, but if we draw that, we actually get 2 shells or 2 orbitals which we can connect to other atoms, so which we can bond, but we actually have this s orbital which is kind of hidden below the p orbitals. We can't really reach it because it's hidden below it. So the s orbital actually can't contribute to our bonding. So we actually just have 2 orbitals which we can bond. So only 2 possible bonds, except we do sp3 hybrid orbitals, which is we have more energy in the p orbitals than the s orbital, so we give a bit of the energy of the p orbital to the s orbital, so we all put them on an even footing. So we actually get from 1 s orbital and 3 p orbitals, we actually get to 4 sp3 orbitals. And those sp3 orbitals look like this. They look like one big bulge and one small bulge, and in the small bulge our electrons are lying, and the big bulges are used to connect our different atoms. So we have 4 connecting bulges, so we can connect to 4 other atoms. So that's quite good and quite nice. So for example, that would mean that we have a tetrahedral structure. The problem is, I can't draw tetrahedral, at least not in this 2-dimensional space, so I actually have to simplify it. So if I would try it, it would look something like this, and this darker bluer color would demonstrate that it's in the background, but I'm actually going to simplify the whole thing. So from a tetrahedral, that means 3-dimensional structure, I'm going to simplify to a 2-dimensional structure with this trigonal planar. And you should remember, and especially you chemists should remember, that it's not actually trigonal planar. It's actually tetrahedral. I'm just simplifying it for the sake of being able to draw it myself. Now let's look at this crystal, and once again, actually this would look differently, and you should definitely look at diamond crystal structures. They're awesome. Actually, there would be a further connection up and here down and up and down and up and down, and there would be this alternating connections up and down, and additionally to that they would actually not all be in the same plane, but these ones would be a bit more up and these ones would be a bit lower, so there would actually be a change in that. I can't draw for shit though, so we have to deal with this. So let's talk about N-doping. And this silicon thing here, this silicon crystal does actually not do anything, because it kind of doesn't do anything. There's no electron right here, there's no positive charge here, it doesn't do shit. So it can't transport charges, so it's not a conductor. But if we dope it with, for example, phosphorus, it actually can start, and we are going to explain why. So we have an impurity atom here, which is, for example, phosphorus, and the only thing it needs is 5 electrons, then it's an impurity atom, and then we can use it, because it only needs 4 bonds. So one electron is actually going to be free. So the thermal energy can knock that free electron out of this phosphorus atom and onto another silicon atom. So when it gets there, it can actually travel free because of the thermal and Coulomb energy. And you would think, oh wait, now this is negative, now this is positive, it already gets back there. But if the thermal energy is bigger than the Coulomb energy, it can actually travel further. And there's another effect called the M&I effect of atoms, which contributes to that being possible. So it's actually not as hard as you would think. Now phosphorus usually has 15 protons and 15 electrons, and silicon normally has 14 protons and 14 electrons. Now this phosphorus right here throws 1 electron away onto this silicon atom. So this phosphorus atom has actually fulfilled the octet rule, and it matches quite nicely into this structure because it has these 14 electrons on the outer shell. But the electron is now on the silicon atom. So the silicon atom is now charged negatively because it has 15 electrons and only 14 protons, and this phosphorus atom is actually charged positively because it had 15 protons and only 14 electrons. 14 electrons is the right number, but 15 protons is just a bit of wrong, so it actually stays positive, and it likes to be that way because it likes to have only 14 electrons. Now the additional electron is going to get kicked around because no one really wants it. So, for example, it can travel up there, and really by this point it only moves by the forces are applied to it by thermodynamics and electrodynamics. So it's actually just moving because there's a positive charge, for example, right here, or a negative charge right here, or maybe because the thing was quite hot right then and it just liked to move in that direction. In the end though, what we should remember is that we have a positive impurity atom and a negative charge wandering about. That's the important part. Negative silicon or negative charge moving, so we have N doping, N negative silicon, negative charge moving, and a positive impurity that's left behind, which is not as important as the negative charge moving, which is why it's called N doping and not S doping, for example. So let's look at another Si crystal, and let's now take the opposite. Let's now dope it with P, so we want a positive charge. How do we get that? Well, we don't take an additional electron, we take 1 less electron, which is, for example, aluminium. The 1 less electron, which is 3 electrons, 1 missing from 4 electrons, actually means that it can't really create this bond, because for this bond it would actually need 1 more electron to fill this gap. But it doesn't have that, so there's a missing part in this bond. So it actually takes from another silicon atom, helped by the thermal energy, and it actually takes the electron from another atom. So let's look at that. For example, from up here, it takes the electron. The electron is going to be put down here to repair this one, to repair this bond, but this bond is being destroyed in the process. So the electron actually jumped or skipped from up here to down here. And it seems, and it only seems, like a positive charge actually traveled from here to here. And if we do that again, it actually seems once again as if a positive charge was traveling, while in fact only a negative charge was traveling in the opposite direction. So we should remember that actually it's a negative charge moving in the opposite direction when we think it's a positive charge moving in this direction. We talk about these positive charges right now as holes, and these are just the negative left behinds. So the hole wanders by, once again, the thermal and the Coulomb energy, so the thermal and the electric energy, or the thermal and electric force, and it really looks like the positive one is moving, but actually it's the electron skipping or jumping around. So we are going to use the positive charge anyway, but we always have to remind ourselves that's actually the electron moving in the opposite direction. Now there's one little quite interesting thing that's actually not that important, but it has some importance. So if you stumble across it, you know why. That's creating and destroying bonds is slower, so the positive charge actually moves slower than the negative charge. So the positive holes move slower than the negative electrons. And once again, we have positive Si, positive charge traveling, so we actually have p doping, and there's a negative impurity left behind. So positive charges moving, p doping, negative charges moving, n doping. Now from a site called homophacins.de, I've actually got you some nice things, which is, for example, this applet between a p and an n junction. So we actually put n-doped stuff and p-doped stuff right next to each other. And we get this one here. And that's what we are going to later call a diode. A diode is nothing else, or in our case nothing else, than a p-doped and an n-doped silicon crystal next to each other. So let's just start. Oh, what the hell is happening? So the gray things here are the aluminium doped, and the orange things, or the yellow things right here, are the phosphorates. Now, if we create an electron that can move, we have a light blue thing. If we create a hole that can move, we have a light red thing. So light things, lightly colored things, can move, while the darkly colored things can't. So the dark red things is the left behind positive impurity, and the blue thing is the dark blue thing is the left behind negative impurity. And we actually see some explosions right here. And what are those explosions? Those explosions are the so-called recombinations. And the recombination is nothing else than we have an electron and this hole, which is just a bond that's not complete. We can use this electron though to fill the bond that's not complete. So an electron and this hole right now make a normal silicon once again. So after we use the electron and the hole, we actually get just the normal silicon once again. So after this explosion is over, there should be nothing left. And you see, nothing is left after it is gone. So the hole and the electron cancel out because they're, in quotation marks, the polar opposite. Now after letting it run for a time, we have minimized the amount of recombinations like those, and actually after a while there's none happening. I can't wait as long, but after a while, trust me, I've tried it, there are no recombinations anymore. If there are no recombinations anymore, we actually call that a barrier layer, because this acts like a barrier. I'm going to show you the charges, and you see this charge here, this layer right here, is charged -10. So for an electron to come down here, it's quite difficult because it's repelled by 11 times the negative charge. So it's actually quite hard for an electron to come down here. And to get up here is also quite hard because there is a charge of +6 preventing those holes from going up, and a charge of -9 or -10 preventing the electrons from coming down. So by missing, and this one is important, by missing electrons and missing holes, we actually get a barrier layer. So missing electrons plus missing holes equals barrier layer. That's important. Because when we now put a field into here, and we feed it electrons and we feed it holes, we're actually going to see that we are going to get recombinations once again. So I fed it right now some electrons, and I fed it right now some holes right here by sucking out the electrons down here and by putting new electrons into it right here. And we're actually going to see that recombinations are going to be more and more frequent. And what does that mean? I say that means that charge is actually running. The charge is actually running from up here to down here. Why do I say that? Isn't it that nonsense? Well, it actually is not nonsense, because the hole that traveled up here to the middle is actually an electron that has traveled from the middle to here. So if a hole recombines with an electron at some point, the electron actually has the additional distance from the hole added to it. So it actually moves until here and has the additional distance from the hole added to it, which is from here to here. So the electron in the end actually travels from up here to down here. So in the end, we actually move charges from up here to down here. So it's actually just a charge running through. So it's actually just current. Let's now though stop helping it, but instead just do the reverse of it. Right now, I am sucking the holes where holes would be needed, and I'm sucking the electrons where electrons would be needed. Because the N layer needs the electrons, and the P layer needs the protons to sustain their non-existence to sustain the combinations, because otherwise there's going to be a barrier layer. If it can't sustain the recombinations, there's going to be the barrier layer. And we see right here quite a huge, gigantic, enormous barrier layer is created by putting the opposite charge right here. So by sucking the holes where holes would be needed, and by sucking the electrons where the electrons would be needed, we create an enormous barrier layer. So this is why, if we talk about diodes, we actually say that you can only travel in it in one direction, sorry. So if we take the negative and add it to the N, and take the positive charge and add it to the P, it works. Current is running. We're feeding the holes where the holes are needed, and we're feeding the electrons where the electrons are needed. But if we do it in the opposite way, and we feed holes where electrons are needed, and we feed electrons where holes are needed, there's no current running anymore. So we can actually just pass current through it in one direction. There's no way to run current in both directions. It's impossible, completely impossible. So right here we have a symbol of a diode, which is just, oh, the current can pass through here, but it can't come back. So that's why there's this arrow. This arrow is basically demonstrating the current can go into one direction, but not into the opposite direction. Let's talk about PNP transistors. And I'm quickly going to do this drawing again to explain it to you. We actually have 3 new names for these transistors, which is, we have an emitter, a collector, and a base. The base is some current that we can put into the middle, and the emitter is sending electrons and the collector is taking electrons. So the emitter is negative, the collector is positive. But we can also do it the other way around. So we can take the emitter on the right side and the collector on the left side, or we can take the emitter on the left side and the collector on the right side. We're going to just look at it, what happens. So negative wants to positive, and we're starting at P and then N. So the P is fed with electrons and the N is fed with holes. So that's problematic, because the N actually needs electrons and the P actually needs holes. So actually we have created a barrier layer once again. So it can't pass through here. It could theoretically pass through here, because we would theoretically pass the electrons onto the N layer and the positive holes onto the P layer. And we can look at it on the other direction, and we're going to get to the same result. From the P layer and the negative part, it doesn't work. The N layer, positive, does work. But the N layer and the negative does work, and the P layer and the positive does work. So we are actually creating a barrier layer depending on which direction our emitter is coming from. The same goes for our NPN collector. So right now I'm going to draw the E and C once again. So right here we have the N and we're doping it with electrons, and we have the P, we're doping it with holes. That's good. That's what we want. But right here, if we go a step further, we actually have P and we're doping it with electrons, and we have N, we're doping it with holes, so that doesn't work. So we're creating the layer on another level. So here we created the layer on the left, and here we create the barrier layer on the right. So it's actually, once again, it's blocking it. So once again, we are blocking it on both sides, because you could actually imagine it as diodes. You can actually imagine that right here you have a diode that only points to the middle. So both diodes point to the middle right here. Sorry, that was for this one. for this one, both diodes point in the middle, because you can always pass through the first one, but you can't pass through the second one. From this side, you can pass through the first, but you can't pass through the second. And from this side, you can pass through the first, but not through the second. And this one is actually the opposite, which is just both diodes pointing outwards. So this is quite problematic. You can't pass current through either of these. So why would these make sense? Because you can actually make them pass current. As we saw for a diode, you can make diode pass current by selecting the right current, the right direction. How can we make that? We can't do that. We have a given direction. We can do that by using the base. With the base, we put charges in the middle. For example, this N layer is in desperate need of electrons to sustain the recombination. So we actually just put electrons in here. This P layer is in desperate need of holes, so we actually just put a positive charge in here. And what happens is, it allows the electrons to go through. And once again, from Homo faciens pointer DE, I have another applet. And right here we can just start it, and it's not really going to do much. But let's just add a voltage to it. And we just added a voltage to an NPN bipolar transistor, which is the right one, and we actually have the collector on the right side, which is the lower example, and we actually should see that recombinations happen here on the left side, and on the right side there's a barrier layer, and we see right side barrier layer, nothing, on the left side recombinations. There was one, there should be another one, come on, right here another one, and so on, and there, and there, and there, and you see left side recombinations, right side nothing. So actually no current is running at all. Now if we increase the base voltage, however, so we say, oh, we feeded some holes, you see the red dots appearing, we feeded some holes by adding a positive charge here, the red one marks that positively, and then we see that some electrons actually managed to squeeze through. This one squeezed through, this one squeezed through, this one, and you see that electrons actually passed through. Which is the important part. We actually get a current from here to here. And of course, most current is still used for the recombinations. So most current still goes up there. And I'm going to talk about it a little bit later again. And we can actually do the same for our PNP transistor. So this is PNP transistor was just the charge activated. So we have this upper example right here. The emitters on the right, the collectors on the left, the positive collectors on the left, the emitters on the right, and we see the barrier layer is being created on this side. We see there's nothing literally happening there, and sometimes there are some recombinations on this side, which is this arrow that works. So let's just add some base voltage. Let's just add some electrons in the middle, and what you're going to see is that this applet doesn't have the functionality to actually display holes coming through. There's actually going to be about 0 holes coming through, or maybe if we wait 2 hours, maybe one is going to do it. But basically, this applet right here has a tiny problem, which is that it's too doped. And I'm going to show it to you right down here. And the normal rate for doping is 1 to 10 to the power 4, and in this applet it's actually 1 to 48 or 47, I can't remember the exact number. So actually in this applet most electrons are used for the recombination between the emitter and the base, and only a few squeeze through to the collector. But in reality, it's actually all the other way around, because the doping is so different. So in reality, it's actually that only a teeny tiny bit of the electrons from the emitter have to go to the base to make the charges more even, and the rest is just passing through. The rest is just passing through to our collector. So in reality, we actually just need a low voltage between emitter and base, and we can pass through a high voltage between emitter and collector. Now this was a video to bipolar transistors and diodes, and I hope you liked it, and I hope you understood the basic formulas, and I hope we're going to see each other next time. Goodbye. Tschüss.